I'm Anil Kumar, and in this video we'll define an equation to represent a plane when normal vector and distance from origin is given to us. The equation, as you know, is r dot n equals to capital D, right? So that is the equation which we are going to derive in this particular video, where r is the position vector of any point on the plane. N is the given normal vector, normal to the plane. And D is actually a scalar multiple of, I should say, k times d, is a scalar multiple of distance from origin. Okay, so these things are given to us. Then the relation which relates is r dot n equals to d. All right. Now let's see how. Let us consider a plane here. And let us say that the normal from the origin is kind of like this. Okay. And we'll take this normal to be d distance away. We'll use small d. D distance away, right? So the distance from the origin of this plane is d. And now let us consider any point P on the plane. Okay, so let me take a point. Let me just connect this and take this point P. Then R is my position vector OP. So R is OP for me, right? OP is R. Now as you can see here, any point on this plane will be relating with the distance from the origin and this normal vector. So that's the whole idea. To derive, let us connect this point. This is called the foot of this normal on the plane. Let us call this point X. Okay. Now, in this this vector diagram, as you can see, we can relate OX, OP, and XP. That forms a triangle, right? Vector triangle. So we can relate them all. So let us say that we are given n as the normal vector. In that case, n divided by the magnitude of n will give us unit vector n. So this is the unit vector which is normal to the plane, right? Unit vector normal to the plane. Why did I take unit vector? The idea is that we have distance from the plane given to us. So along this line, if the unit vector is n with this hat, in that case distance OX can be represented by d times, d becomes a scalar quantity, multiple of this unit vector. So you get an idea, right? So we start with the vector perpendicular to the plane. If we find a unit vector, and now we can say d times that unit vector is OX, correct? What is OP? OP is the vector R for us, is R. Now, we can actually relate PX in terms of OX and OP, right? So what we can write here is that PX, P to X is OX, take away OP. So Px can be written as Ox, which is d times unit vector, right? D times unit vector minus OP, which is R, right? So that is Px for us. Now, as you know, OX is normal to the plane. So any point on the plane, when you join them, it will be at right angles, correct? So from here, we can actually use the knowledge of dot product to relate OX and Px. So we have OX dot Px as equal to 0, since they are at right angles. Now we have developed what OX is. OX is right there, d times n. Px is this, right? So we'll substitute these values. So Ox is d times normal vector dot Px, which is, let me write in brackets, d times normal vector minus r, equals to 0. R is the position vector, right? If you open this bracket, you get d square n dot n minus d unit vector dot r equals to 0. Now n dot n is 1, unit vector, right? So 1, 1 is 1 in the same direction. So we get d square minus, or you can say, you can write equal to also, and you will rearrange that later, d n dot r equals to 0. Now we can rearrange it. So we can write this as d n dot r is equals to d square. Let me take all this to the right side and write down the relation. So from here, d n dot r is equals to d squared. So we can write n unit vector dot r is equals to d, right? Cancelling 1d, correct? That is what we can do. Dot product is scalar, so that is also equal to r dot n, which is d. So we have related the position vector with unit vector, unit normal vector, and the distance. Now, we can always multiply this. This is a very important relation. First, let me highlight this relation, right? So if you are given a unit vector from origin and the distance, that is how they are related. But normally, we are just given the vector, right? So vector will be scalar multiple of this, right? So in general, you will be given, let's say, k times n unit vector, right? So it will be k times d. Now, let this be the normal vector given to us. So I'll rewrite this as r dot n. The normal vector is without the cap. The normal vector is equals to k times d. Let me write this as capital D. So that becomes the equation of a plane which relates to every point on the plane when normal is given to us and the distance from the origin is given to us, right? So that is how we can actually derive at a relation. Now let's apply this and take up an example. Okay, so let's take some value for position vector p and some normal, right? So in general, let us say if I have n, normal from origin is, well, any normal, but you can always place it at origin, right? Let's say the normal vector is 1, 2, 3, right? Just general. And let's take a point P, and OP will be its, O to P will be, let's say the point is, which is R for us, let's say 1, minus 2, 4, okay. In that case, OP is R, right? So this is R for us, the position vector, and that is the normal. How do we find the equation of a plane? So we can do R dot n is equals to D. R is 1 minus 2, 4 dot N is 1, 2, 3, let's say, right, is equals to D. So 1 times 1 is 1, minus 2 times 2 is minus 4, 4 times 3 is 12, equals to D. And that gives us 4 plus 4 take away 12 take away 4 is 8 and then 1, 9, right? So that gives us the value of D as 9. Is it okay? So now we can write equation of the plane as R dot the normal vector given to us 1, 2, 3 equals to 9. Do you get an idea? So R dot 1, 2, 3 equals to 9 becomes the equation of the plane, right? Okay, so that is how you can get equation of the plane. Let us extend this question now. Now, if you are given this equation, you need to find distance from origin. That's the distance of plane from origin. How will you do that? Now, what we noticed was that if I have unit vector times the position vector, dot product I should say, dot product of position with unit vector, I get the distance from origin. So let's find the unit vector. The vector is 1, 2, 3, whose magnitude is how much? So unit vector will be the vector divided by its magnitude, right? So this is the unit vector. So in our case it will be 1, 2, 3 divided by square root of 1 square plus 2 square plus 3 square. Is it okay? Which will be, let me extend on this side, okay? So which will be 1, 2, 3 divided by square root of 1 plus 4 plus 9, correct? Which is 1, 2, 3 divided by 14 square root. Is it okay? So that becomes the unit vector. So to get the unit vector, we have to divide both sides by square root 14, right? So let's do it. So if I divide this side by square root of 14 and also this by square root of 14, what I get is R dot unit vector, and that should be equals to D. Do you see that? So the distance from origin is 9 over square root 14. Do you get an idea? Right? So we can find D. In this particular case, we have D equals to 9 over square root 14. Right? So that is how we can find distance from origin also. So I hope in this video you understand how to derive an expression for the equation of the plane, and also an example how to find out the equation of the plane. So we found the equation of the plane, which is kind of like this, right? And then to get the distance from the origin, the idea is to write that normal vector as a normal unit vector, right? Once you do that, you straight away can read the distance from origin. That's the whole idea. So it's a very powerful equation which we are going to use many times. So try to understand how we derive and how we can apply it. So I'll take a few videos and I hope the concept will be absolutely clear. I'm Anil Kumar. You can always share and subscribe to my videos. Thank you and all the best.